Every time you stare at that gorgeous, vibrant screen on your phone, your laptop, or your TV, you're actually looking at millions of tiny little molecules working like crazy. But what if I told you that most of the energy we're pumping into them is just gone, stolen by this tiny, microscopic thief before it ever even gets a chance to become light? Well, today we're going to dive into this amazing piece of chemical detective work from the Journal of Physical Chemistry C. Scientists thought they were hot on the trail of a secret energy shortcut, one that promised to make our screens practically perfect. But oh boy, what they actually found was something else entirely. All right, so first, let's meet these supposed heroes of our story. These are a new class of materials that have scientists just incredibly excited, and, for a really good reason. Okay, check this out. This little guy is called 2PT-ZBN, and in the world of these new MRT-ADSC materials, it's an absolute rock star. Seriously, think of these molecules as the Lego bricks for the next generation of TVs and phones. We're talking ultra-vibrant, super efficient displays.
So what's the big deal, right? Why all the excitement? Well, these materials are kind of the whole package. They make colors that are just unbelievably pure and vivid, and they're almost 100% efficient at turning electricity into light. I mean, that lets us build OLED screens that are over 30% efficient, which is a massive leap forward. But there's a mystery hiding behind just how they pull this off.
See, scientists had a theory. They had a prime suspect for why these molecules were so good. They were convinced there was some kind of secret energy shortcut going on, but they had to prove it. Okay, to get this, we need a super quick chemistry lesson. Don't worry, it's easy. Just picture a molecule as a tiny little factory. When you feed it electricity, a whopping 75% of that energy gets dumped into what we'll call the waste state, a triplet state. It's just stuck there. It can't make light. The whole goal is to get that energy over to the on state, the singlet state, because that's what actually makes the light we see. So the big question is, how do you rescue all that wasted energy? So how did they think it was happening? Well, scientists suspected this process called HRISC. It's a mouthful, stands for High-Level Reverse Intersystem Crossing. The theory, and you can see it in this diagram here, is that HRISC acts like a secret shortcut. It takes energy from these hotter, higher energy triplet states and zaps it directly back into useful, light-making singlet energy. If this was true, man, it would be a total game changer. And look, this wasn't just some wild guess. As the paper itself says, the whole scientific community pretty much agreed that these higher energy triplets were the key. So the stage was set to prove it, once and for all. Okay, so how in the world do you catch a process that happens in less than a trillionth of a second? Well, you set a very, very clever trap. And their setup was just brilliant. First, they hit the molecule with a steady blue laser. The goal was to just keep filling up that waste triplet state. Then, bam, they fire an ultra-fast laser pulse. It's like giving the molecule a perfectly timed kick to boost that energy up to the higher triplet states, exactly where the HRISC shortcut was supposed to happen. And then they use this incredibly fast camera to watch for an extra flash of light. That little flash, that would be the smoking gun, the proof that HRISC was doing its job. So, the trap was set. They ran the experiment. And the results, well, let's just say nobody saw them coming. This was it, the moment of truth. Did the trap work? Did they see that telltale flash of light? Was the whole HRISC theory right? Nope, not even a little bit. The bombshell result was, get this, at most, a measly 3% of the energy was being rescued by HRISC. It was basically a no-show. The hero of our story, that secret shortcut everyone was betting on, was almost completely absent. So wait a minute, if HRISC isn't saving the energy, where's it all going? The prime suspect was innocent, and that meant there had to be another culprit out there. A real energy thief, hiding in the shadows. And just like that, the investigation took a sharp turn. With RYC off the hook, the scientists had to find the real reason all this energy was vanishing. And what they found was a thief that operated on a timescale that is just almost impossible to imagine. So everyone meet the real villain of our story, internal conversion, or IC for short. See, instead of letting HIR do its job and recycle that precious energy into light, IC just grabs that hot triplet energy and dumps it right back down to the lowest waste state. All that energy is just lost as useless heat. It's the ultimate energy thief. And why does the thief always win? Well, it all comes down to a race. And honestly, it's not even a fight. The high-risk shortcut? It's fast. We're talking over 1 billion times per second. But internal conversion? It's about 100 times faster. Think about that, 100 billion times a second. The energy thief is just way too quick. The good guy never even has a chance. And the scientific reason IC is so crazy fast comes down to something called the energy gap law. Basically, the energy gap between those higher triplet states and the lowest one is just too small. It's like, imagine water at the top of a really short, steep waterfall. It's just way too easy for it to fall down. And in our little molecule, when that energy falls, it's lost its heat. Game over. Now, I know what you might be thinking. This sounds like a failure, right? But in science, proving a theory wrong is often way more valuable than proving it right. Because now chemists know the real enemy they need to fight. So what's the big takeaway here? First, the problem isn't that the HRISC shortcut is broken. It's that this internal conversion thief is just ridiculously fast. So that means all the future research has to focus on one thing, designing new molecules that can slow down IC. And how do you do that? You have to re-engineer the molecule to make that energy gap bigger. Basically make that waterfall much, much taller, so it's harder for the energy to just fall away as waste. You know, as the researchers themselves put it, these findings really challenge the core assumptions that have been driving this field. It completely reshapes our understanding of how these incredible molecules actually work, and it gives us a clear roadmap for how to make them even better. And that, of course, leaves us with the next huge question. This research didn't hand us the final answer on a silver platter, but it gave us something way more important. It gave us the right question to ask. The hunt isn't for a secret shortcut anymore. Now the real hunt is on to design a molecule that can finally outsmart the energy thief.